Now it's time to move on to look at that solar and lunar phenomena, the eclipse. From the earliest days, humankind has been observing eclipses, sometimes with complete terror, but sometimes with curiosity. Depicted in petroglyphs and cave paintings, we think we have found images of eclipses dating back to about 3340 BCE in Ireland, but also in petroglyphs in places like Mexico. The earliest written accounts coincide with the earliest written accounts of anything. Records of eclipses go back as far as we have writing. In ancient Babylonian records and ancient Chinese, eclipses are often mentioned as very significant events that occurred in the daily lives of those people. One of my favourite stories was this guy, Thales of Miletus. Now, he predicted an eclipse, and it's not clear how he did that at that time, but he predicted that there would be. And he found that these two warring people, the Medes and the Lydians, basically people that lived in modern-day Turkey, some that lived in the west, and some that lived in the east, fighting for supremacy. Now, acting to try to stop the conflict, he told the Medes that the Lydians could darken the sun and win the war, and it would be an omen that they were going to lose. And he told the Lydians exactly the same. And then when the sun went dark in a solar eclipse, the fighting stopped and everyone ran for their lives. A great story. Whether or not it actually happened exactly like that, we will never know. Now, in the Middle East, eclipses are connected with omens affecting kings. A solar eclipse in Syrian and Babylonian traditions predicted the death of a ruler or a king or a major military defeat. An eclipse was a defeat. And so, in the Gospel, there is the story of an eclipse occurring at the crucifixion. Now, there was no eclipse at about that time, in about that place. So we think that it's used as a device to explain the idea of the death of a ruler or a defeat. But fast forward 800 years, and the mayor of modern-day Mexico, they were very good predicting solar and lunar eclipses, tracking the cycles of the moons and its nodes, understanding exactly how long you would have to wait before an eclipse was seen in the same place. And because their writing has been recovered, the Mayer codices, such as the Dresden Codex, we've got tables and tables and tables of eclipse prediction. And they predicted so far forward, in fact, that their calendars went all the way from 800 CE to 2012, leading in 2012 to some people thinking that the Mayans had predicted the end of the world. You know, it's just as far forward as their calendar went before they thought this is all a bit pointless. Now, eclipses have played a minor part in some major world events. The discovery of much of the southern hemisphere, for example, occurred when Captain Cook sailed around the South Pacific. And he was doing so because he was trying to observe, one, a transit of Venus, and two, a solar eclipse. Along the way, in his voyages, he discovered many, many places. Now, it's not necessary to say that he wasn't the first person to see these places. Many of these places had indigenous populations already. It's not even correct to say that he was the first European person to see these, because some of these places had been sighted, but ultimately the accounts of those had kind of been lost to history. Captain Cook was the first person to properly document the existence of these places, which he found on these voyages. And so he is credited with the discovery of New Zealand, the east coast of Australia, many Hawaiian Islands, Christmas and Easter Islands, South Georgia, South Sandwich Islands, the Pacific Northwest coast of America, and the Antarctic ice pack. So in these voyages that he went along, he discovered all of these places before he was killed in Hawaii. Sometimes there are amazing echoes in history where something happens and then something happens again, and the similarity between the two is astonishing. So let me tell you about this. In 715, an elderly Isaac Newton was at his house inside the Tower of London when he was overseeing the Royal Mint. And he was quite elderly, and he was looking out of the window, and there was one of the best eclipses this millennium to go over England. Now, his good friend and colleague Edmond Halley, who was Astronomer Royal, and also the person that named Halley's Comet, wanted to test out some of Newton's predictions to see whether or not his universal law of gravitation and his solving of the puzzle of the motion of the moon was correct by seeing whether or not the eclipse would happen as it was predicted. And indeed it did. That Edmond Halley proved that Isaac Newton was correct through the observation of an eclipse. Now hold that thought, because we're going to come back to it in just a second. But first I want to talk about Francis Baily, an English astronomer who in 1836, after Edmond Halley, was observing an eclipse and noticed that just before it happened totally, that the sun glinted in little tiny droplets of light around the edge of the moon. And we'll talk about these later, but I put these in as a historical point right now because we are going to get to them later, and we'll do a proper explanation of them when we get to that point. So in 1715, Edmond Halley used a total solar eclipse to prove Isaac Newton correct. Now fast forward to 1919, and the same thing happened again. That Albert Einstein, in the first major revision of Newtonian gravity, put forward a new idea about gravity called relativity. And he thought that the position of a large mass, like the sun, could actually distort space and time. And that what would happen if you looked at a large mass like the sun is that the background field of stars would be shifted due to that distortion. However, we can't normally see this because the sun is too bright to see the background stars. But it was thought that during a total solar eclipse, if you photographed the star field, you could indeed observe the distortion. If that distortion was observed, then Einstein's relativity would be proved correct. So enter Sir Arthur Eddington, English astronomer and well, a very, very impressive physicist in his own right. He voyaged to Principe off the coast of Africa, and alongside other astronomers in Sobral, they took precise measurements of the star positions around the 1919 eclipse. As a consequence, they found that the star field had been distorted behind the sun. Proof, the first major proof, and the thing that slingshotted Albert Einstein into global fame, found by observing the star field behind an eclipse. Now, we don't need to listen to that, because that is indeed me. That is me from a quarter of a century ago as a small boy, observing the total solar eclipse that crossed Cornwall in 1999. That was the last total solar eclipse visible from the United Kingdom, and it will be the last one until 2090. So we're not going to see another one, not in my lifetime, but maybe in yours. So that there was a fantastic thing for me to observe as a young astronomer, to travel all the way down to Cornwall and see totality. Now, at another point, I'll allow you to see that video, but at the moment it's just far too embarrassing for me to show you in this clip. So we must now talk about what conditions need to be met for us to see an eclipse. Well, we have to be careful first because there are two types of eclipses, a solar eclipse and a lunar eclipse. We'll talk about a solar eclipse first. Now, a solar eclipse is where the moon gets between the sun and the earth, and in that alignment, the shadow of the moon falls backwards onto the surface of planet Earth. Now, for the moon to be between the Earth and the sun, it needs to be a new moon. We must be looking at the unilluminated side of the moon. We're looking at the back of the moon, whereas the other side of the moon is being lit up by the sun. And it has to be a straight line. The slightest bit of not straightness, and what happens is the shadow will not fall onto the surface of the Earth, but will fall off the Earth instead. So why don't we get an eclipse every new moon? Well, most of the time, the moon passes above or below the sun's disk every new moon. It glides on by. And that's because the moon has got a 5-degree tilt of its orbit relative to the solar system. And that means lots of times it just sails above or below the sun in the sky. But there are two places on its orbit, the places that we call nodes, where if a new moon coincides with a node, we get an eclipse, because a node is where it crosses the plane of the solar system. And if it is there at the same time that the sun is the other side of it, then the alignment is right for us to get an eclipse. And we actually have about 2 of these every single year. So somewhere on Earth, there will be a solar eclipse about twice a year. Now, it may not be that you are under the main part of the shadow, the umbra. You could be in the penumbra, the part of the shadow that is only partial. And from those places, you don't see the moon completely obscure the sun. You see the moon only obscure part of the sun. It takes a little bite out of it. And these are all my photographs of various different partial eclipses. Some of them are more complete than others. It's an amazing thing. Over the course of about 2 hours, you see the chunk taken out. You can't see the moon, but you can see the shape of the sun change because the moon is obscuring it. But yet, even with all of these, you don't particularly see much of a change in the brightness on the ground. It still stays quite bright. It's also possible that not all of those eclipses, when we have 2 per year, for example, not all of them might actually create a total solar eclipse on the surface of the Earth. Not only is the moon's tilt of its orbit at 5 degrees to the solar system, it's also an ellipse, which means sometimes it's slightly further away from the Earth than at other times. And when the eclipse coincides with it being at a further point in its orbit, at apogee, then the moon is actually slightly further away, and being further away makes it smaller in the sky and too small to cover the sun's disk. And so what you get is, even when the moon is right over the center of the sun, is that the sun is still visible around the edges. We don't get totality. We don't get a really dark shadow on the Earth. That's called an annular eclipse. And so this does sometimes happen. It's very disappointing, but indeed quite a few eclipses are like this. Now, what we've learned is, as the moon is drifting away, a greater proportion of the eclipses are going to be annular, until they're all going to be annular, when the moon is too small in the night sky or in the day sky to actually obscure the sun. Now, to understand a little bit about what we expect to see during a total solar eclipse, we must understand a little bit about what the sun looks like. The sun's outer layer, the part of the sun that is visible when we're looking at a sunset, for example, is called the photosphere. That's the place where the sun ceases to become opaque and becomes transparent. It's the point which appears to us almost like a solid surface, even though it's not. And from this point, that is the edge of the sun as far as we're concerned. It's super bright. We can't look at it with the naked eye. And on this surface, we see things like sunspots. And erupting from this surface, we see things called prominences, these great big loops of material ejected in the magnetic fields out into space. Now, this is the part of the sun that is completely obscured in a total solar eclipse. Now, do you remember Baily's beads? I told you we'd come back to them. As an eclipse is progressing, and as the moon covers more and more of the sun, then what we find is there is a phenomenon that occurs just before totality, just before it gets completely dark, where the sun is shining very, very close to the edge of the moon. And the roughness, the mountains and the valleys on the edge of the moon allow the light in some places to sneak through and some places not. So what you're literally seeing here, the Baily's beads, you can see this photograph at the bottom, it's shining through the valleys, but is being obscured by the mountains. Those little black dots in between the beads, they're the mountains of the moon. That's an amazing thing. And in the closing seconds before totality itself, we see the diamond ring, where there's just one tiny bit of sunlight shining around, and it looks like a diamond ring. At this point, the excitement is so incredible. Having been there in 1999, this is the moment where literally you cannot breathe with excitement about what is about to happen. For during a total solar eclipse, the solar photosphere is completely covered. A number of things happen. the sky around you goes completely dark. You actually physically see the shadow of the moon race across your head really, really fast. And around you, it turns nighttime and the stars come out. The birds start roosting, sheep start lying down. It all gets really, really strange. A blast of cold air comes as suddenly the sun is extinguished. And around the sun in the sky, there's just this massive, deep black hole of the moon. And around the edges, you can see a part of the sun that is not normally visible, the solar corona extending several times the diameter of the sun out into space. For you see, that part of the sun visible at sunset, that's not all of the sun. The sun extends to 2 or 3 times bigger than it looks in the sky. But because it's kind of transparent, the sunlight shines through it, and you don't normally see those outer layers, except in a solar eclipse. And here is an incredible photograph, just so that you can really understand what's happening. The contrast has been turned up, and you can see in the darkness, there's the moon. And it's the same face of the moon, look, there's the man in the moon, that always looks down on the earth. And why can we see it? It's being illuminated by earthshine. A little tiny bit of the light hitting the earth is reflecting onto the moon, allowing us to make it out. Now, you can't see this with the naked eye, it just looks black. But with photography like this, you can pull out the details and you can see all of that really strange. The sun is not spherical. The sun extends like a giant streaming starfish into the solar system. And exactly the shape of that starfish depends upon whether or not the sun is at its most active or at a quieter moment in its cycle. For you see, the sun is a variable star, which we'll talk about later, but it actually has a solar activity cycle that lasts a period of years. Sometimes when it is very active, what we see is that the solar corona extends in all directions in great big streamers. And when the sun is much less active, it just tends to stick out on either side, much, much less corona. Now, the solar corona itself is really strange. It's actually hotter than the surface. The solar photosphere is about 6,000 degrees, but basically it's so thick and not transparent that the energy struggles to do much. As soon as the light gets to the surface and can rip through the outer coronal gases, it has the effect of smashing into those coronal gases and literally imparting a huge amount of energy, meaning that the solar corona is itself millions of degrees C, hotter than the surface beneath it. Now, with any eclipse, we can make predictions about exactly where the shadow will fall on the Earth. We call that the path of totality. Either sides of the path of totality are regions which will observe a partial eclipse. Now, trust me, if you're anywhere near an eclipse, you have to travel into the path of totality. It may not be very wide. A very good eclipse will be very wide, but some eclipses, it's a very narrow band, and you have to ensure that you are right in the middle of it. Now, looking at eclipses for the next 15 years, on the left-hand side, you can see one of the best that is going to happen, or the only one that really goes across anywhere in Europe, is the August 2026 eclipse that goes through Spain. But you can travel to these places that have eclipses and you can observe them. And it's one of those bucket list things that as an astronomer, as a human being on this planet, you should try to observe an eclipse at some point in your lifetime. Now, that path of totality, the shadow falls on it, not all at the same time. The shadow ends up falling at one part and travels down the path of totality from the west to the east as the moon goes the other way. Now, it's possible, if you're in a fast enough aircraft, to stay and keep up with the shadow as it goes across the ground. Now, in 1999, there was a passenger aircraft that was capable of flying at supersonic speeds called the Concorde. Now, the Concorde went and flew out and met the shadow out in the Atlantic Ocean and then flew back across the path of totality and observed an eclipse that lasted for over an hour. But for people on the ground, they get possibly 2 minutes of the eclipse, and it's over in a heartbeat. And this is a photograph of an eclipse from space. So here on the International Space Station, looking down, the shadow of the moon, there's the region of totality, a black area, an area of nighttime in the middle of the day. What a fantastic photograph. A key thing with an eclipse, it's like observing the sun at any other time. The sun is exceptionally bright and will damage your eyesight, even if you look at it just for a split second. So the best thing to do is one of two things. Either you can get yourself some proper eclipse glasses, which block out 99% of the sun's light, or you observe the eclipse through the projection mode. Now, projection basically means you let the sunlight fall through a small hole onto a sheet of paper. Now here I'm holding up a colander, one of those things that you wash vegetables in, and every single hole acts as a hole through which we can get a projected image of the sun. And you can see on the ground all of those little partial eclipses, all visible. What you'll even find is as the sunlight goes through little holes in between the leaves on a tree, you'll get little tiny crescent suns all over the ground. That's the safest way to observe it. Now that's quite enough about solar eclipses. Let's talk about lunar eclipses. Now the Earth's shadow stretches out behind the night side of the Earth all the time, right past the lunar orbit. It goes so far back that if the moon is at the right place at the right time, the moon would pass into the Earth's shadow. Now most of the time it doesn't. Most full moons are full moons and the moon stays completely illuminated. And that's because of that 5-degree tilt of the moon's orbit. If the moon is at one of its nodes and it is crossing the plane of the solar system at exactly that point where it is also a full moon, then it will fall into the Earth's shadow. Now the Earth's shadow is made of two bits. There's a bit called the penumbra, when part of the sun is obscured, and the part called the umbra, where the full sun is obscured. It's basically, when it enters the umbra, it is for the moon entering totality, the same as like what we saw in a solar eclipse. Now, a lunar eclipse takes place over many hours of a night time, so it's get the hot chocolate out and a blanket and or keep coming back to it. Looking at this image here, the top right is the normal moon, and what you see as time goes on is first of all a little bit of the penumbral shadow, it's like darkening of one of the edges of the moon, and then, and quite clear, you see the umbra. Now what's happening here is you can see the umbra, the darkest part of the shadow looks slightly red until eventually, when it is total, the whole moon is blood red and significantly darker than normal. Now the reason for this is even though the sun's light is completely obscured, what is illuminated is the atmosphere of the Earth. And so from the point of view of the moon, what you can see is a blood red ring in the sky of Earth's atmosphere being illuminated like a sunset, but all the way round the Earth. Now this is enough light to cast a red light onto the surface of the moon. Unlike a solar eclipse, whose totality is only visible in that really narrow band for a lucky few, a lunar eclipse is visible to anybody that can see the moon. So basically anyone that is on the night side of the Earth when the eclipse is occurring, bearing in mind that it happens at full moon, and the full moon is basically overhead, at night time only, because it has to be on the opposite side of the Earth to the sun. Think of the alignment. Anyone that can see the moon from anywhere on the Earth at that time is going to see the moon get plunged into the Earth's shadow. So these, as a viewer experience, are a lot more friendly for wider participation. Now we spoke at length about the historical significance of solar eclipses, but lunar eclipses have had their moment of fame as well. Aristotle observed that the shadow of the Earth on the moon was round, and he also noted that it was always round. It was never an ellipse, it was never a flat line, and it was one of the major pieces of evidence that came to him that the Earth itself was round. You can't have a round shadow always forming on the moon from a flat object. It has to be spherical. Now, there was, of course, other people, like Eratosthenes, that measured the curvature of the Earth. It all formed a picture that to the ancient Greeks made them believe that the Earth was indeed round. So this notion that the ancients believed that the Earth was flat, well, actually, the ancients that took observations quickly realized that the observations showed that it wasn't. And finally, what does a lunar eclipse look like on the surface of the moon? Well, we have now sat landers on the surface of the moon. This is Blue Ghost. Sat there and observed a lunar eclipse from the surface. So first of all, you can see there's the spacecraft at the bottom, and on the left-hand side, there's its view of the sun normally. And as the Earth gets in the way, you can see top right, first of all, it goes blood red all over the moon, and second of all, in the sky, replacing the sun, is a red ring of fire as the sun's light gets refracted through Earth's atmosphere, creating a ring of sunset, casting its red light onto the lunar surface.